Unit 1 of Corona Chemistry, where we are going to be teaching you the content and curriculum that is utilized in my own high school, which is in a suburb of Dallas, Texas. And so we're going to give you a good amount of information. This is information that is valid for both regular and honors chemistry, honors or pre-AP, whatever your terminology is that you use. So if you're not from our school or our district, you're still welcome here. It's still valid information. Sit back, kick your feet up, enjoy yourself, okay? Let's get into it. Unit 1 is an incredibly boring unit, just to put it just plainly out there for you. It's not chemistry. We're setting you up for the chemistry that is soon to follow, right? So Unit 1 and Unit 2 are really just laying the framework, laying the foundation for us for when we really start talking about elements and their components and their properties in Unit 3, stuff like that. So the title of this unit is Scientific Method and Measurement, okay? We are going to be collecting data through various labs and activities for chemistry, and we need to know how to process this information, which is why we need to be able to utilize the scientific method and the measurement. But first, let's go into a few terms. As for how these videos are going to work, if this is the first video that you've tuned into with Corona Chemistry, you will find Google links to both the notes and the slides that I'm utilizing here in this video today just below the video. So feel free to grab your own copy of those. Feel free to make your own notes. And yeah, let's get into it, okay? So looking at our chemistry, the definition of chemistry. Definition of chemistry is the study of the composition of matter and the changes that matter undergoes. So why would you be so excited to learn about chemistry? Well, take a look around you. Everything that you can see or touch is made of matter. Everything is composed of these little things called atoms that each have their own unique set of properties, and then when combined with other atoms, then it creates this whole new array of properties and all that. And what is not to just be fascinated about with that? To learn about what is going on around us and why these things work the way they do, that's pretty freaking cool. And matter is anything that has mass and occupies space, and so when I'm thinking about that, that's practically everything that I can think of. What isn't matter? Well, there's really only a few exceptions. Light is one of those, and you might be saying, oh, I can see light and all that. Light is energy, right? And energy is another really, really great example of something that isn't matter. And light is one of those things that we see every day. It's super palpable. You can't touch it. You can't necessarily feel it, right? It's not actually occupying space, and it certainly doesn't have mass. However, light is kind of funky too, and that's why there's this kind of little physics debate here, where it behaves both as a wave, which doesn't have matter, but it also behaves like a particle, and particles are matter. So it's kind of spicy there. Light, something that doesn't have matter, yet sort of behaves like it does have matter. And light is something that we will very briefly talk about in future units, but not necessarily what we're going to be talking about today. Just a little tidbit of information there. When we're looking at other basic definitions, these are terms that you surely have heard before actually getting started with chemistry. We have the difference between mass and weight. Now, there is a difference. However, because all of our conversations are going to be taking place on planet Earth, it doesn't actually matter here. Mass is the amount of matter in something, and weight is how much whatever planetary celestial body that you are residing upon at that current junction is pulling on you. Well, because we're always going to be on Earth, our weight, it's always going to be the same, okay? We're not going to magically fly out to Jupiter for Unit 4. We're going to be sticking around here, okay? So, going into the scientific method, I remember that this is something that they've been slamming into your brain since like 3rd grade of elementary school. And I remember the only project I ever failed in school, and this is, elementary, middle, and high school, just a subtle brag there. The only project I ever failed was in freaking 5th grade, where we were tasked to create our own science experiment. Well, you better believe the innovative mind of myself. I set out to make Alka-Seltzer and baking soda and vinegar rockets. Oh, man. Made little rockets in the driveway in the front yard, and my goodness, those puppies flew. But my teacher, I'm not going to say her name. I'm not going to say her name, okay? But I know you're out there. Maybe you're watching here today, but I know you're out there. You ruined me for a short period of time, but I came back with a vengeance, and I said to myself, I'm going to be so successful. And that's what I did. But anyways, I failed. I got a 53 on the project. I got the trifold diorama of all the scientific method, the hypothesis, the conclusion, the data, all that. I thought it looked spicy. I thought it just looked fantastic. but my teacher did not agree. What a sad, sad time. But either way, the scientific method gives you a process with very plainly laid out steps for you to follow. And you can utilize this for any kind of experiment that you're going to be pursuing. But the first thing you got to do is what are we looking at here? We have to state a problem. And a problem doesn't mean that the nuclear reactor is about to explode and kill everything around it. No, a problem is a question that you want to solve or potentially find an answer to. Okay, so what do we want to find out? That's the problem. Well, step two, let's research a little bit. Let's just not go into this blindly. Okay, is there even a problem here? Maybe if you research a little bit, you'll find out that someone's already solved this. Not saying that you can't, also do an experiment that someone has already done in the past, but it's not as enticing to do something that someone has already done before. And then we are going to state our hypothesis. And in chemistry, we're very picky about this. Your hypothesis, which is your educated guess about a potential solution to this problem, must be written in an if-then format. If this condition is met, then this result will ensue. Example, if I drink more coffee at night, then I will have more trouble falling asleep at night. We're not, really explaining why that is in our hypothesis. It's a very plain example, right? We're going to let the experiment do the rest of the talking for us. But we have to have an if and a then in our statement, okay? Then we are going to actually go on to the experiment, which if you've never done that before, you have to consider several details. And the reasons why is we're going to look at these other terms right here, control and variable. Control, and you can have several controls in your experiment, are parts or aspects of the experiment that do not change. You want to control them, okay? Because if we're going back to the example we had before, if I drink more coffee at night, then I will have more trouble falling asleep at night. Well, what if my diet consists of just an entire family-size bag of Sour Patch Kids every night, along with the 3 cups of coffee? Well, what's keeping me up at night? Is it the Sour Patch Kids? First they're sour, then they're sweet, then they're gone? Or is it the coffee? We don't know. However, if we control our diet and we're changing other aspects of it, aka our variable, well then we can contribute or we can attribute our results to that changing variable. The variable is the part of the experiment that changes. And to really clearly interpret our results, we want to make sure that we are only testing one variable. So let's say I do dabble in the Sour Patch Kids with my diet at night. Well, if I've already been doing that for years, well then I better not change it, right? And I better not, douse my Sour Patch Kids in Red Bull at night as well. I want to know if it's the coffee that is affecting my sleep at night. Anyways, we've got 2 different types of variables here. Independent variable is what you are manipulating. And if you are graphing this, you will typically find your independent variable on the x-axis. What you are manipulating. Independent, meaning that it's not really listening to anything else, okay? It's independent of everything else. A lot of experiments, this is time, right? What is changing over time, that sort of thing. And so you're not literally manipulating time. Time is just sort of happening, but it's what you're using in lieu of anything else. And the dependent variable is what is changing as a result of the independent variable changing. So what depends on something else? So if we're going back to my original example over here, how is my sleep at night or my trouble falling asleep at night? That would be the dependent variable. If I drink X amount of coffee, what happens to the quality of sleep I get or how long it takes for me to fall asleep? Or if I don't drink any coffee, how long does it take me to fall asleep? That sort of thing. So my sleep depends on the amount of coffee that I'm drinking. That sort of thing. I know it's a very term-heavy introduction to this course. I understand it's not the most exciting thing, but you've got to have a foundation before we actually get into the spicy, exciting stuff. Okay? So bear with me, ladies and gentlemen. After we get our results, we're going to make observations. Or sorry, while we're doing our experiment, we're going to be making observations throughout. Okay? And these observations are going to be amalgamated into our results towards the end. And we've got a couple of different observations here. Quantitative versus qualitative. And if you're just saying those words out loud, what words do you hear within them? The beautiful English language has some very awesome word roots and from word to word. And so in the word quantitative, I hear the word quantity. Well, what the heck is a quantity? It is a number. And so a quantitative observation is anything with a number involved. And they always have to have a unit. So This desk is 5 meters wide. It took me 45 seconds to run a lap, whatever it is. A qualitative statement, you hear the word quality in there. Qualitative statements are descriptive, and they talk about a certain quality about whatever you're looking at. Colors, smells, tastes, that sort of thing. You can't put a number to a taste of something. Oh, this Sour Patch Kid tastes 7. It doesn't work, right? And so we are going to use descriptive terms for those qualitative statements. Pretty simple there. Don't get it twisted. Just say the word out loud. What do you hear within the word, okay? Then we are going to write a conclusion. A conclusion here in chemistry, if you haven't done scientific writing in the past, we do also require a very specific format for this as well. Some of the middle schools are roping this into their curriculum. Some aren't, right? And so what we utilize is called a CER format, claim, evidence, reasoning. Okay? You state the claim, right? Your solution to the problem, the answer to the question that you pose at the beginning. You are going to list your evidence that you gain from your results. That doesn't necessarily mean just, copy and pasting your results. It's your interpretations of the evidence. And then the reasoning. This is where the kids get tripped up here. If you don't practice this, you're not going to know what to do whenever it's actually important. Okay? The reasoning is the scientific concept that is going to show why the evidence that you have gathered validates your claim. Okay? A lot of kids just try to take the evidence they just listed in bullet point format and just rope it into complete sentences as their reasoning, and that's not right. That's a waste of ink. That's a waste of my time if I'm reading it, right? If we are utilizing your beginning in chemistry here to set you up for potentially pursuing science in the future, right? Well, then somewhere down the line, if that's the case, I'm not saying that's the case for all of you, right? Somewhere down the line, your scientific writing is going to be hella important, right? You need to be able to communicate a thought, right? Let's say you've made some groundbreaking discovery. Well, if you don't know how to formulate the actual conclusion here to present it to the public, well, then what good is it? That'd be a real shame if something went to waste, right? And so, let's say that you stumble upon a guy with a black eye. Well, what would be a reasonable conclusion? What would be a reasonable claim here? Well, personally, I would say that a black eye is from getting punched and slugged in the face. We're not trying to say, why he got punched in the face. Maybe it's because he ate all the Sour Patch Kids when I explicitly told him not to. Okay, so really it's more fault than it's his fault, not mine, right? But I'm going to say that he got slugged in the face. Well, why does a black eye indicate that someone has experienced a punch to the face? Well, and this might sound like I'm going over the top here. Reasoning behind this, okay? You might be listening along me. I'll go, that's really dramatic, man. Why are you talking like that? No one talks like this. Well, a black eye is really just a bruise. And what is a bruise? A bruise is from the rupturing of blood vessels just beneath the skin. Well, why would that happen? Unless he has some very small physical disease that affects and afflicts only a small diminutive amount of the population globally, then he wouldn't have spontaneous blood vessel rupturing. Blood vessels rupture when they experience physical trauma. Physical trauma in the form of a fist to your eyeball. That's going below, that's going beneath the surface. That's going deeper. That's explaining scientific concepts, right? How it applies to your claim and why the evidence supports your claim, okay? So if it's in chemistry and we're just introduced the concept of density, how does density apply and why does it validate your claim that you have made? Okay, this has been a lot of words and it feels like, maybe we're spending way too much time on this, but I promise you we're not. It takes practice, and that's why if we actually get to meet in person and we're doing these labs post-corona, or who knows, maybe Texas gets especially bold and we do it in the midst of corona. That'd be a spicy school year, right? You're going to get a lot of practice writing these conclusions, okay? So let's move on from there. Theory versus law, just a couple of other terms, right? And pretty common sense as well, right? So a theory is sort of an attempt to explain something that you see out there, whereas a law is an observed phenomenon that has been proven and validated. Your theory is just your attempt to explain some phenomenon that you're seeing out in nature, right? Common sense, we've seen these words utilized everywhere. It's not just in chemistry that these words are utilized here. So let's go into some specifics for chemistry itself. Safety is super, super important as we're going to do several labs. And you've done safety stuff in the labs before in your other science classes, but now you're going to be working with new substances that you never have before. And so safety that is specific to chemistry, I'd just like to point out a couple of things. You should always be labeling the solutions and substances that you're working with in the lab, because a lot of things look like water that will do very nasty things to your body if you don't handle them properly. And if you don't know what you're dealing with, then you're likely to not handle them properly. Second of all, one of the most dangerous things you're going to utilize in labs are various acids of strengths or a variety of strengths. All acids are dangerous, however, some are more dangerous than others. Either way, you want to always handle them like they are going to be, as dangerous as possible. And one of the ways that we do this is we always pour acid into water, not the other way around. And so the way I think about that is always and not when. Always acid into water, A to W, and not when. Like crying like water into acid. And the reason why is because the acid reacts with the water, or vice versa. They are reacting with each other, and it produces a lot of heat. And so if you're pouring a small amount of acid into the water at a time, if it were to produce enough heat to, let's say, splash, well, then it's more likely that the water is splashing out and not the acid. Meanwhile, if you do it the other way around and you're pouring water into the acid, and it produces so much heat, or maybe you're just doing it really sloppily and it splashes, well, then it's more likely that acid is splashing out and melting your hand off as opposed to water splashing out. So always, always, always acid into water whenever you're making solutions in the lab. So let's go on to our first numerical concept for chemistry. Chemistry is a beautiful mix of concepts and math, okay? And so, yes, it's a beautiful mix of both worlds. Let's go into scientific notation, which you may or may not have done before. Scientific notation is a way for us to write either really, really, really large numbers or really, really, really small numbers. Either way, it is so, so, so important to get practice with this so that we know what the heck we're dealing with here. However, that being said, in almost all the calculations that we're doing in chemistry, you're going to have a calculator on hand, and so for the most part, the calculator is going to do it for you. However, if you don't know what you're looking at, well, then that's useless to you. Now, very, very important, the number that is written to the left of the x, the multiplication, the times 10 to the, whatever you're doing with scientific notation, must be between 1 and 10, okay? Including 1, not including 10. It must be between 1 and 10. We just solved these examples for you on the board just a second ago, but there is also a shortcut that I implore you to use. So you should have either a scientific calculator or a graphing calculator. Scientific calculator more simple than the graphing calculator. And both of them are able to do this. Okay? You'll see that both of them have the second button in the top left portion of the calculator. Right? Well, what that does is that allows you to utilize the second option of each button that is on the calculator. Notice that each of these buttons have blue text above them, except for the numbers on the scientific calculator. They only have the one function. Well, if you hit the second function, followed by a button on the calculator with the blue text, it will utilize the second function of said button. And there is a shortcut for this. Some of you might be punching into your calculator times 10 caret and then exponent. There's no need to do that, because there is a shortcut here. And so, if you will see just above the number 7 on both of these calculators, the scientific or the graphing calculator, you will see the comma for the graphing calculator and the x to the negative 1 button for the scientific calculator. If you're taking a look at that, that's the button we're going to utilize. But first, you must hit the second button. And if you'll notice what that blue text is just above each of these buttons, it looks like two E's, two capital E's. Well, what that E represents is times 10 to the. It is times 10 caret all in one button. Okay? And less buttons you're punching into the calculator, the less room for error. I would hate to see you write out all this work on your chemistry test. You did everything correctly just to get the wrong answer because you plugged into your calculator wrong. That would be unfortunate. And so, when we're looking at these next examples on these notes here, we can utilize the shortcut, and the calculator is going to absolutely do all of the work for us. There's no reason for us to make any mistakes here. And so when I'm looking at addition and subtraction, yes, you can utilize times 10 caret exponent and get it correctly, right? I would just be super diligent with parentheses, making sure that each of those terms are separated so that you don't overlap anything that's not meant to be overlapped. But if you utilize this e function in your calculator, right? I'm not talking about natural log e. I'm talking about those two capital E's that I just showed you on these calculators here, right? It just makes things faster, streamlined, okay? And that's the name of the game in a lot of pieces of content in chemistry, right? The faster you can go, the more problems you can hit in a string of time. Let the calculator do everything for you, ladies and gentlemen. Do not stress about these. The calculator is a miracle machine and will do it all. And as long as you're punching in the numbers correctly, it will not let you down. Next, we're going to be looking at special rules for rounding. You might be saying, oh my goodness, that chemistry has their own specific rule for rounding? Yes and no. And I will say straight up, I don't really like this rule. If you're in on-level chemistry in my school, you don't have to worry about it. If you're in honors chemistry, you do have to worry about it, okay? We all learned how to round stuff in elementary school, right? If it's 5 or above, we round up. If it's 4 or below, we stay the same, right? Well, it gets a little weird with one very specific issue you may run into, okay? So the first two bullet points, nothing new. If the next number is over 5, go up. If the next number is under 5, remain the same. But if we run into a rare example of what is known as a perfect 5, where the number after what we are rounding is exactly a 5 and nothing after, we have to pay attention to some rules, okay? For whatever reason, way before you or I was born, they decided that even numbers are awesome and odd numbers are not. So if the number that you're looking at to round would become even, well, then we do it. We want even numbers. But if the number that we are looking to round would become odd, we don't do it. We stay the same. So let's look at a couple of examples here. All right? We're going to round all of these numbers to the tenths place, right? And so we've got various numbers here. They're all pretty close to one another. Some go to the hundredths place, and the very last one goes to the thousandths place. So let's discuss them. We don't really need to go to the dry erase board for this. We're going to round to the tenths place, which means we are going to round to the first decimal place, which means all of these numbers should only have two numbers at the end, okay? So we look at the number 4.56. We're rounding to the tenths place, so the 6 is going to determine whether or not we round up or down, and because it is over the number 5, we round up. So this would become 4.6, okay? We look at 4.42. The 2 is going to decide whether or not we round up or stay the same. Well, the 2 is below 5, so therefore we stay the same, so it's 4.4. All right, nothing weird about that. That's what we're used to. But these next two examples are that very rare example of what is known as a perfect 5. We are rounding to the tenths place, and the number after the tenths place is a 5 with nothing after it. If there's anything after that 5, it is not a perfect 5 because then it's over that halfway mark, and we don't have to worry about it. If it's anything over the value of 5, right, if the next number is a 5 and there's numbers after it, we always round up because it's just past that halfway mark. So this 5 is going to determine whether or not we round up or stay the same. Well, what we need to look at is what is going to happen to this 5 when we round up. If 5 were to round up, it becomes a 6. And a 6 is even. And we like even numbers in chemistry. So this number, 4.55, would become 4.6. Now let's look at 4.45. Well, this 4, we're looking at potentially rounding it up. What would happen to it if it rounded up? Well, the 4 would become a 5. And 5 is odd. Oh, no. We don't like odd numbers, and so we're not going to round it up. So 4.45 would stay 4.4. That's kind of weird, especially when we'll look at the very final example here, 4.451. This is not an example of a perfect 5 because there is a number after this 5. It doesn't matter if there were 20 zeros and then a 1. That is still a value after that 5 and would not be a perfect 5 situation anymore. So no matter what the situation is here, because there's a number after that 5, it's not a perfect 5, therefore we round up. So 4.451 would become 4.5. Kind of weird, kind of tedious, super rare. Okay? Do not always be worrying about this perfect 5 situation, always looking over your shoulder going, oh my gosh, it could happen, it could be here. It's very rare. Okay? If you're in honors chemistry in our school, you will run into it. And if you're from other schools around, I'm sure you'll run into it. I've heard of schools not enforcing it. The college I went to didn't enforce it either. Okay, it's just kind of a weird, obscure rule, but you should be exposed to it. If it's out there somewhere, you should be exposed to it. And that's my philosophy. All right, let's move on to a couple more terms. All right, accuracy versus precision. I'm a big fan of the NFL, ladies and gentlemen. I love football. And I kind of cringe whenever I hear Troy Aikman, announcing for the Dallas Cowboys, and he uses the terms accuracy and precision interchangeably as if they have the same meaning. Why would you have two different words if they mean the exact same thing? Well, they don't have the exact same meaning. Okay? Precision is a measurement of how you can reproduce the same results, how consistent you are. Accuracy is being able to say, I want to hit the bullseye, and I hit the bullseye. Okay? So now let's ask ourselves a couple of questions. Can we be accurate without being precise? Can we be precise without being accurate? Let's present a couple of different scenarios. Bear with me. So let's put this in the context of a real life situation. Okay? Accuracy versus precision. We've got our young man, Dak Prescott, quarterback for the Dallas Cowboys as of now. And he's slinging some pigskins down the field to yours truly. Why is it yours truly? It's because I'm a force to be reckoned with. Okay? I put on my freaking speed shoes. I'm 50 yards down the sideline. They tried to block me at the line of scrimmage. I just ripped past them. Josh Norman could not contain. Okay? I'm sprinting down the sideline. And what does Dak Prescott do? He sees his number one weapon in me down the... Here I go. Here it comes. Dak misses. It's within reach! But my 6'3" stature, I couldn't pluck it out of the sky. So Dak Prescott shoots it just a tad high. Okay? Well, we run the exact same play. They'd never see it coming. Here it comes! Here it comes! Oh my goodness. A little high once again, Dacky boy. Let's, third down, third and long. Let's go big. Let's go for broke. Okay? They'll never see it coming. And what do? We run the exact same play in. A little high. Wouldn't you know? Dacky boy misses the long ball. Who would have seen that coming? Who would have? Michael Gallup maybe, but who would have seen that? Okay? This is an example of precision. Look at how close those balls are together. That's pretty consistent. Did he hit me, the number one receiver in the league, any of those attempts? Not at all. Not at all. However, he certainly reproduced a very similar result. And that's what precision's all about. Precision is not necessarily hitting your target where you wanted it to, but it's being consistent. Accuracy is hitting your target. And so this example over here is an example of precision without accuracy. And if I'm his coach, I'm saying, Dak, listen, my guy, you're so close to being on the money. You just angle this downward just a tad. And you're able to do that every single time because this guy is obviously consistent. He's obviously precise. If we just adjust it the slightest bit, well, welcome to Canton, Ohio. I'll see you at the Hall of Fame. Okay? If I'm his coach, I'm not mad at this result because we can make these small adjustments. If you're all over the map, well, then what are you supposed to do? There's not much to do. So now the other question that we posed is, can you be accurate without being precise? Let's look at another example. So now the question that we are posing is, can you be accurate without being precise? And remember, the very subtle difference is precision is consistency, being able to reproduce the same result, or at least similar results. Accuracy is being able to hit the money. So let's put this in the context of hunting. Now, I myself have actually never been hunting, but if I were to go with my father, this is how I imagine it would go. We're out there. We've sat out there all morning. It's cold in the woods, a little wet. We see this buck come into the clearing. And my pop says, take the shot. Okay, take the shot, he says. So I line it up. And boom! Pop says, oh, okay. A little high, a little left. And obviously, this deer has no survival instincts whatsoever. He just thought that there was some surprise party happening over the next hill. He doesn't think to move at all. He's stunned. Okay? So my pop says, all right. You aim a little down, a little to the right, and you're going to be right on the money. So what do? I adjust, and shaboom! I went right. I didn't go down. Pops goes, just lower it, just a touch, just a tad, okay? But now you got to bring it back left, okay? Bring it back, okay? Take a third shot, third time's a charm, shaboom! We brought it down, but didn't pull it left. So we pull it left. Obviously, we got to pull the gun up a little bit as well, and shaboom! This deer, I don't know how it survived so long. It hasn't moved an inch, or maybe it just knows that I'm just not a good shot, and now I'm out of shots. I mean, if you take the average of all these shots, where did I hit? Smack on the money. Like, I don't know much about hunting, like I said, but that looks like a kill shot to me. However, am I eating tonight? I'm not. That final shot, this final X that we see smack in the middle, would be exactly what we're looking for. That would be accuracy. However, if we take the average of all these shots, that doesn't necessarily mean that that's what the truth is. So, in this example, we were not precise, but we were not accurate either. You cannot be accurate without at least being a little precise. So where do we run into this? What kind of situation are we dealing with here where there's one without the other, right? Because you can, of course, be both accurate and precise. Look at this target here in the bottom right. Look at that. Wow. That guy's pretty consistent. That's a gold medal if I've ever seen one. Well, let's say that you're measuring something on a scale in the lab, right? You're taking the mass of something, and it's, for a fact that it is a 10-gram weight. But you put it on the scale and it says 12.1, 12.2, 12.1 grams. You take 3 measurements. They're all really close to each other. That's precise. That's precision. But you know for a fact that this is a standard 10-gram weight, and it's not saying 10 grams. So at least the scale is precise, which I should certainly hope so. And all it needs is a little calibration, okay? And so the tools in the lab have ways to do that. We can calibrate it back down so that it will actually read the 10 grams that we know it should be showing. So that's what we're dealing with, accuracy versus precision. And this is also why we will do multiple trials of the same experiment, right? We want to see if our results can be reproduced, because that actually shows whether or not we're actually proving our hypothesis. If I just see something one time, I'm not going to say, oh, that's law, right? We have to reproduce it. We have to be able to reproduce it for it to be a law. Either way, that's accuracy versus precision.
Quarantine log. I'm not sure what day we're on. It's currently July, and that's all I know. I'm pretty sure we're so far into this that we've actually abandoned the Gregorian calendar. Every day is now called Blur Day. There's no days of the week. There's no order. There's just tomorrow.
So we just took some measurements in the lab. What's next? What do we do? Well, there's lots of things we can do. And the first of which is we can see how far away we were from where we were supposed to go. And now you might be asking, well, how the heck do we know what we were supposed to get? What measurements were we supposed to see in the lab? Well, there's lots of different ways to do that. The most common way of doing that is a term called stoichiometry in chemistry, which is something we'll learn how to do a little bit later on in this course. But either way, once you have this, what is called a theoretical yield, aka what you were supposed to get in the lab, we can see how far off we were utilizing a percent yield equation. Then we can also see how wrong we were by calculating for percent error. And these are, two sides of the same coin, right? They feed into each other. If I've got a 94% yield of what I was supposed to get, well, then I've got a 6% error. Yes, you can get more than a 100% yield. Is that chemically possible? It shouldn't be. But you're not a perfect scientist. You're brand new to this. Therefore, you're going to make mistakes. And so maybe you put in a dash instead of a sprinkle of whatever ingredient you were starting with in the beginning. It's just like cooking. And therefore, you make more than you were intending to. Therefore, your percent yield could be over 100. So let's look at this example before we solve it on the board. Suppose you produce 4.5 grams of product and you were supposed to produce only 4.2 grams of product. What is the percent error of this experiment? The only way you can possibly mess this up is if you don't understand what a theoretical value is. Because if we look at this percent error equation, we have absolute value bars on the top part of the fraction, which means it doesn't actually matter what order we put the numerator of the fraction because it's always going to turn out to be positive. We always have a positive percent error here. However, if we mess up which value is the theoretical versus which value is the experimental value, well, then our answer is going to be wrong. So just double check whenever you're looking at this. Your theoretical value is what you were supposed to get. So when I'm looking at example 1, that is supposed to be 4.2 grams of product that I'm producing. Just look at the language of your question, and you'll always be able to deduce that. So let's solve it on the board now.
Working out our first couple of examples that require calculations on the board for you is going to include percent yield versus percent error. And we have the two equations for you right here. They are two sides of the same coin. They work with each other, right? They all essentially add up to 100 because whatever my percent yield is, as far away as it is from 100, that is what my percent error is going to be. For example, if I make 95% of what I was supposed to, then that's a 5% error. If I make 105% of what I was supposed to, meaning more than I was supposed to, then that means it's still a 5% error. So looking at these equations, once again, for percent yield, what you really want to make sure you're doing is making sure that actual is on the top, so what you actually produce in the lab, and theoretical is on the bottom. And remember, theoretical is what you are supposed to be getting, okay? It is the value that is proven by science that we should be getting as long as we're not making any mistakes in the lab. And then just like with both of these equations, since they're both percentages that we are solving for, we're going to multiply by 100 in the final step. Notice in the percent error equation, we have absolute value bars on the top, so it doesn't actually matter what order you put the numerator of the fraction in, because it's always going to result in a positive value. The only thing that you can do to mess this up is if instead of putting the theoretical value on the denominator, you put the actual value in the denominator. So let's look at example 1 in your notes. Suppose you produce 4.5 grams of product, and you're supposed to produce only 4.2 grams of product. What is a percent error? So obviously we're using this equation for this example, but you have to pay attention to the language. Suppose you produce 4.5 grams. That is what you actually produce. It's not what you were supposed to, it's what you produced. So that is our actual. And then 4.2 is what we were supposed to get. That is the theoretical. So we are going to plug and chug 4.5 minus 4.2, put it in absolute value bars, and we're going to make sure that it is the 4.2 that we put on the bottom, because that is theoretically what we were supposed to get. So we plug into our calculator, we have 0.3 in our numerator after doing that subtraction, divide by 4.2, and multiply by 100. And so that is going to give us 7.14% error.
Our next question is, what is the percent yield of the lab experiment if you got 22.0 grams of copper and you were supposed to produce 23.4 grams of copper? So this is going to utilize the other equation that was on the previous slide, percent yield, which is just what you got in the lab, aka the actual yield, over what you were supposed to get, aka the theoretical yield. If you mix those up, you're going to get the wrong answer. And just as with every other percent equation that you've dealt with in your life, you always end it by multiplying whatever your value is at the end by 100 to turn it into a percent. So let's quickly solve it.
Example 2 in your notes is, what is the percent yield of a lab experiment when you got 22.0 grams of copper and you were supposed to only get 23.4 grams of copper? So what we produce is the 22 grams. What we were supposed to produce is the 23.4 grams. So we're doing the percent yield equation here. Make sure that we don't flip where these values are going. The 22 is going to go on top, and the 23.4 is going to go on bottom. Just like with percent error, we are going to end by multiplying by 100. Simply plug and chug into your calculator. And we get 94.0%. We made 94% of what we expected to.